The next theorem we're going to talk about and actually prove is really pretty remarkable. We know that if you have two countable sets, A and B, then the cross product of A and B is also a countable set. But this increases that greatly. This theorem says that if S is a subset of the natural numbers, essentially it could be any countable set, and it might be easiest to think of it as just being the natural numbers. Non-empty subset. If this is an indexed family of countable sets, which means that every single one of the A sub S's is another countable set. It could be a set of integers. Every one of them could be the set of integers. So if this is an indexed family of countable sets, then, maybe I should, here's the conclusion of the proof, or of the theorem, then the union of all of those countable infinite sets is also countable. So to prove that, well, actually, let me first show this picture. I'm just kind of assuming now that the set S is the natural numbers, at least for this picture. So we have an A1, A2, A3, and it goes on forever. A1, I'm naming the elements as A11, A12, A13, ... an infinite number of elements. The second set, I'm naming A21, A22, A23, and so on, an infinite number of elements, and similarly for A3 and going on in both directions. So it goes infinitely in that direction, infinitely in that direction. So we have what looks like an infinite matrix for those of you who have taken linear algebra. And the moral of that story, of this theorem, is that if you union all of these elements together, it's still a countable set. So in order to prove that, we're going to have to find a function that maps all of these numbers into the natural numbers, or into any countable set. So the start of the proof goes like this. We will find a function. Here's what we're looking for. This is a countable set from the previous theorem. We will find this function that maps every element in the union into in cross in, and it's going to be 1 to 1. So no element over here, every element here will get mapped to a distinct element in cross in. All right, since each individual A sub S is countable, I'll go ahead and say for all S in capital S, there exists a 1-to-1 function, or there exist 1-to-1 functions, one for each one. I'll call them F sub S, that maps A sub S into the natural numbers. And that's true for all values of S. Again, we can say that because this is an indexed family of countable sets. So each function, each set AS has a corresponding function, F sub S. For each X in the element of this set, the union, for each X in this set, we're going to define the function f as f of x is equal to m comma fm of x. I have to define what m is, where m is the smallest number in S, capital S, such that x is an element of A sub m. Okay, what's that saying? Well, the number m, see, it's possible that in all of this infinite number of numbers that say, for example, those two numbers are equal to each other. We want to choose m to be the smallest number in S, where x is in A sub m. We're going to choose this row because it's a higher row, it's got a smaller index number. If these two numbers are the same, we're going to define it to be that term. Since x is an element of the union of the AS's, x is an element of AM, not for all of them, but for at least some. For some M in the set of all S. That's the definition of union. If X is in the element of the union of all of these sets, it has to exist in one element. In one or more of those sets. Since S is countable, we may choose M to be as small as possible. And actually, I got ahead of myself a minute ago. This is where we're choosing this set over this set. We're choosing this element over that one, if there are any repeats. And this is possible to do, small as possible. That's possible to do by the well-ordering principle. This simply shows that f is well-defined. It is a function. It is a well-defined function. To show that it's one-to-one, well, we're going to prove it's one-to-one just like we prove every other function that we prove is one-to-one. Suppose for two values x, y, in that union of the AS's, that the following is true, that f of x equals f of y equal to L comma R. Okay, I used L and R for left and right. So we're just supposing that f of x is this ordered pair, f of y is exactly the same ordered pair. Well, if it's a one-to-one function, we're going to end up saying that x and y are also equal to each other. That's what we're going to prove right now. Thus, x is an element of AL. Think of L as the row number in that matrix. And y is an element of AL. And this number here, the y number, R, is equal to f of x, or I should say fl of x, which is fl of y as well. But f sub L is a one-to-one function. So since FL is one-to-one, we know that x is equal to y. We see that x is equal to y. Thus, f is one-to-one. And to finish it off, we'll go comma, and the union of the AS's is a countable set.